Yes, Assalamualaikum. This is your Thermodynamics 2 class. This is your lecture number 8. So can anyone confirm that what's appear on my screen right now?
Lecture number 8, Chapter 9, Gas Power Cycles.
Okay, thank you so much. Okay, so starting from your chapter number 9 now. Okay, so previously we already talked about vapor power cycle. Okay, so now we have to go to gas power cycle, which is your chapter number 9. So before starting, we have to know that what is the difference between gas power cycle and vapor power cycle. As I have already discussed in the previous lecture, that in vapor power cycle, your working fluid is always in a uh, liquid phase, or either it will be in a two-phase region. However, in a gas power cycle, it is always in a gaseous phase. Okay, so this is the basic difference between gas power cycle and your vapor power cycle. However, when we are talking about that how to produce more efficient power by using the power cycle, so either we have to use gas power cycle or vapor power cycle. So this is the main question. So in order to make more efficient power cycle, we have to combine both of the cycle. So there will be a combination of gas power and vapor power cycle in order to produce more work and more efficient power plants as well. So in this lecture, we will start from chapter number 9 and we will look at how to thermodynamically analyze these gas power cycle and what are the different types of gas power cycle by which we can produce some useful work. Okay, so this is the basic idea for your gas power cycle, that if you see that your spark ignition engine in your automobiles, these are working on your gas power cycle. However, there will be a mixture of fuel and air inside it, but whenever we have to analyze gas power cycle, we have to assume something. Okay, so we will look for this these assumptions, that what are these assumptions before we start a thermodynamic analysis of gas power cycle. So this is the basic example of your gas power cycle, which is your spark ignition engine. Okay, so starting from your application, so the application of gas power cycle are very wide. So it will be in your jet propulsion and aircraft systems also. Okay, where we have to produce power to drive the compressor and small generator to power the auxiliary equipments also. Then there will be a power generation process. We can use the gas turbines to generate electricity, and also if we can use in conjunction with the mean, we have to use the gas power cycle and vapor power cycle both at the same time. We can produce power also. Okay, we can produce alone as well, but if we can produce more power, if we want to produce more power, we need to combine both of these cycles. So there will be application in marine application as well. Okay, so we have to get the power in order to drive these large ships. Okay, so this is also by using the gas power cycles. Okay, so then there will be different types of gas power cycle. The basic one is the Otto cycle, which is used in the petrol engines. There will be a diesel cycle, which is used in the diesel engine. Then there will be a Brayton cycle, which is used in the gas turbine. Also, there will be two more also, which we will discuss later on. That what are these? So, but you have to just remember that these are the three major type of gas power cycle, and also there will be one more, that is Carnot cycle, which we already know that this is the more efficient one, and we have to start from this, that how to achieve the maximum efficiency, which is equal to the Carnot cycle. Okay, so we will start with the Carnot cycle also, but before this we will look for the assumption which are required for your power cycle analysis. Okay, so these are called the air standard assumptions. So these are the air standard assumptions which we need to assume something before we have to thermodynamically analyze the gas power cycle. So these are the assumptions. The first one is the working fluid is air. Okay, so the working fluid is always air. Whenever we say that there will be an air standard assumption, and which continually circulate in a closed loop and always behave as an ideal gas. So this is the first assumption. The second assumption is that all the processes that make up the cycle are internally reversible. So it means there will be no losses in your processes. Okay, so these are the reversible one. Third one, the combustion process is replaced by the heat addition process from an external source. Okay, so this is similar thing which we already see in the Rankine cycle also. We can replace your combustion process with your heat addition process. Okay, a similar thing happened over there as well. The fourth one is that exhaust processes is replaced by a heat rejection process that restores the working fluid to its initial state. So in comparison with the Rankine cycle, we use the condenser one in order to reject the heat. So here we replace it with the heat rejection process for the exhaust process. Okay, so if you can see this figure which is shown over there, so the figure A shows your actual cycle, okay, actual combustion process. So in the actual combustion process, the air is going in, fuel is going in, here it will be mixed together and it results in the combustion products. However, once we are talking about the ideal cycle, there will be a air, there will be a heating section where we have to produce some heat, and then there will be and the exit one also there will be a air. So your working fluid is always air, okay, in your air standard assumptions. So we will see that how this work when we are going to solve the problems also. So then there will be a cold air standard assumption. This is another assumption. This is only valid when the constant specific heat at room temperature, when your working fluid is considered to be air and the constant specific heat at room temperature is 25 degrees C. So this is only valid for these conditions. Then there will be an air standard cycle. So a cycle for which the air standard assumption, so these all four assumptions are valid. This is called air standard cycle. Okay, so now coming towards the first cycle, which we will know that which is the efficient one, Carnot cycle. So we will look for the Carnot cycle, then we will go further to deal with the other types of cycle as well. Okay, so starting from the Carnot cycle, so in your Carnot cycle, it composes of four totally reversible processes, which means that it utilizes all the energy that is either be a heat source in the work or there will be a less rejection of heat as well because it is a reversible process, and it consists of four processes. One is the isothermal heat addition process, another one is isentropic expansion process, then isothermal heat rejection process, and isentropic compression process. Okay, so these are the four processes. So we will draw this Carnot cycle on TS and PV diagram so that you can get the better understanding out of it. So we will start with the PV diagram over there. Okay, so coming from the first point, isothermal heat addition process. So it is mentioned from its name that it is an isothermal process. It means that temperature is constant. So for example, if we start from TS diagram, so we have to just make, for example, this is your point number one, and it is an isothermal heat addition process. It means that there will be temperature will be the constant one. Okay, so you can just draw a straight line to show isothermal heat addition process. Okay, so similar thing for the PV diagram, we also have to draw the same process on the PV diagram. So you will see how to draw it. So as you know that whenever there will be isothermal heat addition, it means that after the heating process, your volume will increase and your pressure will decrease. So for example, your first point is over there, there will be any pressure. Okay, so it means that if your volume will increase, so your second point will be on your right side and your pressure will also decrease. So it means that you can just draw some point over there. So this is your point number 2, and then you can just join. Okay, so this is your 1 and 2 on the PV diagram. So now coming towards your second isentropic expansion process. So it is mentioned that it is an isentropic process. If we have to draw on DS diagram, it means that your entropy is constant. And whenever there will be an expansion process, it means that your temperature, which is at the initial column that is at T2, so it will be decreased. So it means that this point will be over on this area. So you can just join this 2 and 3 and it will be your expansion process. So similar thing we have to draw on the PV diagram as well. So for 2 to 3, if there will be expansion process, it means that your volume increase in your cycle, in your process, and then your temperature will also decrease. Okay, so your point number 2 and here you can just draw point number 3. Okay, because it will increase the volume and your pressure is decrease. And then you can just join like this. So now isothermal heat rejection. So it is an isothermal process, and whenever there will be a heat rejection, your entropy will decrease. So it means that your point number, you can call this as 4, and you can just join this line by using a straight line, and then we have to draw on the PV diagram as well. So when there will be a heat rejection, so it's mean that your pressure will increase and your volume will decrease. Okay, so this point you can just draw over there. So your pressure is increased and your volume will move toward your left side. Okay, so now the one state which is remaining is isentropic compression process, which is between 4 to 1. So if it is an isentropic, it's mean that this will be a straight line, and now your cycle is complete. And for 4 to 1, again, you know that if there will be a compression process, this means that your volume is decreased and your pressure increase. So it's mean it will again go to your point number 1 towards your increase in pressure, and your volume is also towards decrease. Okay, so these are the processes which are involved in the Carnot cycle, and which is drawn over the TS diagram and PV diagram. Okay, so we will just say that this is your Q in, which is your Q added, this is your Q out, or you can also say Q rejected, and here there will be a, okay, so this is your expansion process, so 2 to 3 is your expansion process, and 4 to 1 is your compression process. So again here 4 to 1 compression, 2 to 3 expansion, this is your Q in, and this is your Q out. Okay, so this is how you have to draw the Carnot cycle on the TS and PV diagram. Okay. Another important thing is your efficiency for your Carnot cycle. So we already know your efficiency for your Carnot cycle. You can just say this 1 minus lowest temperature over highest temperature. Okay, so we already know that in order to increase the efficiency, we have to increase this area under the curve to get more work output, and in order to get the maximum efficiency, either we have to take this temperature higher for your Q in. Okay, so either if we move this point 1 and 2 to above, we can increase the area, or either we can decrease the temperature where the heat is rejected, so still we get the maximum efficiency out of the cycle. But important question is why we do not use this Carnot cycle if it is more efficient, so in our gas power cycle as well. But here the main issue is that the process 1 to 2 and your process 4 to 3, these are isothermal heat addition and isothermal heat rejection. So it is not practically possible to make such a process where there will be a heat addition and on the isothermal, keeping the temperature constant. Also, it is not possible to reject the heat, making the process isothermal. So that's why it is not practical to make this Carnot cycle using the our practical gas power cycle. Okay, so these are the clear diagrams which is shown over there. You get the better idea about it. So this is your PV diagram for your Carnot cycle, and this is your TS diagram. And here it is mentioned over there isothermal heat addition, expansion process, heat rejection, compression process. And again, this is that for both ideal and actual cycle, the thermal efficiency increase with the increase in average temperature at which heat is supplied to the system, or with a decrease in average temperature at which heat is rejected to the system. And if you have to draw the systematic diagram for your Carnot cycle, you can say that it composed of two compressors. One is the isothermal compressor, one is the isentropic compressor, and two turbines. One is the isothermal turbine, and second one is isentropic turbine, and which are linked together like this, so that you can make the Carnot cycle. But practically, it is not possible to make such type of system. Okay, so now coming towards your, 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 okay, so now coming towards your some basic terms which we use in your engine. Okay, so which we need in order to analyze different sort of problems when we are solving problems for this chapter as well. So if you see this one, this is your piston cylinder arrangement. Okay, so this is your cylinder, this is your cylinder, this is your piston over there. Okay, so the main important thing is there was some terminology we have to use. Okay, so we start with the bottom dead center. Okay, so if you can see, this is written over there, bottom dead center. Okay, so bottom dead center where the piston position where volume is maximum. Okay, so when this piston, which is shown over there, will place on the bottom dead center, so it's mean that the volume inside your cylinder is maximum at this point. Okay, so this is called the bottom dead center. Similarly, when this piston moves upward and reaches to your top dead center, which is mentioned over there, here the volume inside your cylinder is minimum. Okay, it is not zero, it is minimum. Okay, so this point is called the top dead center. Okay, so there is still some volume over there, and that volume which is still remaining when the piston moves towards top dead center, it is called the clearance volume. Okay, so which is your, you can represent V2, which is the minimum. You can see in this picture as well. So this is your piston when it is at BDC, then it's moved towards TDC, and your remaining volume will shown over there, and this volume is called the clearance volume. Then another term which we have to use in your engines are the compression ratio. So compression ratio is basically your maximum volume. So your maximum volume is at bottom dead center. So here your volume will be maximum, and here your volume will be minimum. So it is the ratio between these two, volume maximum and volume minimum. You can also say volume at BDC and volume at TDC, or either you can say V1, V2, or specific volume at 1 and specific volume at 2. Okay, so now another term which we use is the displacement volume. So displacement volume is basically the difference between your maximum volume and your minimum volume, which is the volume at BTC and volume at TDC. And you can say V1 minus V2. Okay, so now another important term is which is called your bore. Okay, so this is written over there, bore. Bore is basically the diameter of your piston, you can say, and internal diameter of your cylinder as well. Okay, so these are denoted by the bore. Okay, so if your bore is given, it's mean in your question or in your problem, so it's mean the diameter of your cylinder is given internal diameter, or your diameter of the piston is given. Or if you have to find the area, you can easily find the area of your piston or area of your cylinder as well, internal area, by just pi d square over 4, and this d is your bore. Okay, now another important point is your stroke. So stroke is written over there. So stroke is basically the distance when it's moved from bottom dead center, when your piston move from bottom dead center to top dead center. So it is length between these 2 points. Okay, so bottom dead center and your top dead center. Okay, so this is called a stroke. If you have any question, you can also ask me. Okay, so another important terms which we use frequently in analysis of the engines and engine cycles, so which is called the mean effective pressure. So in order to understand this well, we have to see this PV diagram. So if you just notice over there, so you can just see this area which is shown for your area under the curve for one cycle. Okay, so for example, this is the area for your real cycle, and there was some pressure over there. So for example, you can call this P1, you can call this P2, you can call this P3, or this call you can P4, or you can call this P5. Okay, so there are some pressures by which you have to create this type of cycles. Okay, but in order to understand and in order to compare the performance of two different engines, we do not need to calculate, we do not want that we have to calculate all time this area under the curve for each one. So it will be a very difficult thing. So what we have to do is we just take the average of all this pressure, and this average is called mean effective pressure, which is mentioned over there, mean, so it's mean the average pressure. Okay, and we just draw one reference line by using this mean effective pressure, and we just say that this is your V minimum, this is your maximum volume, which is at BDC, and we just denote there will be an area under this mean effective pressure line, and the area, for example, this area is A1 and this area is A2, and this A1 is equal to A2 under this mean effective pressure. Okay, so in this way we get better understanding and we can get the comparison for the performance of two different engines as well. Okay, so and this is the imaginary pressure. This is not a real pressure, but we still get the better understanding that because it is very easy to find the area under this curve rather than area under this curve. So for mean effective pressure, if we can just have to develop an equation, so it will be W net over volume displaced. So volume displaced is your volume between BDC and DDC. Then there will be another term, mean effective pressure into piston area into stroke. So piston area, I already told you that you can just calculate from your bore length. Okay, it will be given in your question, or either it will be not. You can easily find from this relation as well. So stroke is also the length between this BDC and TDC, which is called your stroke. Okay, and then these two things, which is your piston area and into stroke, is called displacement volume. And if in your question it is mentioned that you have to find W net and your mean effective pressure is given and displacement volume is given, you can just multiply these two terms and you will get W net easy. And then mean effective pressure we can also represent by W net over V maximum minus V minimum, or either it will be W net over specific volume maximum minus specific volume minimum as well. Okay, so these are some important terms for your engine. So now coming towards the cycle which we frequently see in our spark ignition engines. So our spark ignition engine or our automobile engines, which is your petrol engine, work on the Otto cycles. Okay, so and this Otto cycle, which consists of 4 different processes. So first one is your isentropic compression, constant volume heat addition process, isentropic expansion process, and constant volume heat rejection process. Okay, so we will draw on the TS diagram as well, that how this pressure and how these 4 processes looks like, and we have to draw on the TS diagram or PV diagram as well. So we will start with the PV diagram. This is your pressure, this is your volume, and here there will be a TS. Okay, so starting from your first state, which is your isentropic compression one. So if you notice that it will be an isentropic process, it means that your entropy is constant. So if we draw on the TS diagram, so you can say that your entropy, for example, this is your point number 1. So entropy is constant, and so it will be a compression process. It means that temperature of your working fluid increases over there. So this is your point number 2. Okay, similar we have to draw on the PV diagram as well. So for 1 to 2, so either it will be we know that it will be a compression process. So for compression, the volume decreases. For example, this is your point number 1. So it will go towards your left side, and your pressure will increase. Okay, so it's mean that your point number 2, you can just say it will be lie over there, and you can just join these 2 points, and you will get 1 to 2. Okay, for second process, which is your constant volume heat addition process. So if we draw on the TS diagram, it will be looks like that if it will be a heat addition process, it means your temperature is increase and your entropy also increases. So this means that this 2 to 3 will be over there. Okay, so this is your heat addition process, and similar on the PV diagram as well. So it will be mentioned that it is a constant volume. So it means that your 3 point is similar to the volume of 2. So it means it is in line with this one, and your pressure increases whenever there will be a heat addition. So it means that this point number 3, and this is again a straight line. Okay, so now the third process, which is your isentropic expansion process. So if you draw on the TS diagram, so your TS diagram, it will be mentioned as the isentropic process, and your expansion process, your temperature decreases. So it means that your point number 4 will be somewhere over there, you can say. and then you can just join these two lines, and it will be 3 to 4 your expansion process. And for your isentropic expansion, your volume will increase, okay, when there will be expansion, and your pressure will decrease. So if there will be a point 3, so your point number 4 will be less than this point number 3, or it will be towards your right side, because there will be an increase in volume. So this is your 3 to 4. Now coming towards your 4 to 1, which is your constant volume heat rejection process. So if it will be a heat rejection process, it means that your temperature, which is at point number 4, will be less than this one. So you can just join over this one and like this. So this is your 4 to 1, and it is a constant volume heat rejection. So your pressure will decrease and your volume will be constant. So this is your 4 to 1. So now you can just mark some points over there. So on the PV diagram, so you can say this will be your Q in, on the, here will be this Q out, and here there will be 3 to 4 is your expansion one, isentropic expansion, and here there will be compression process, which is your 1 to 2, and similar thing is over there. So this is your compression, this is your expansion, 2 to 3 is your Q in, and 4 to 1 is your Q out. Okay, so this is how you have to draw the TS and PV diagram of the Otto cycle. And whenever you have to solve this type, G.
सर ये राइट वाले टीएस ग्राफ के अंदर 2 से 3 के पॉइंट जो है मुझे इसका समझ नहीं है, इसका काइंडली बता दें.
ओके, मैं आपको रिपीट कर देता हूँ.
जी.
Okay, so 2 to 3 is your constant volume heat addition. Okay, so it's mean that whenever there will be heat addition, your temperature will be increase. Okay, and when there will be increase in temperature, your entropy will go towards the increasing order. Okay, so it's mean that this point, which is from 2, will be your point number 3 will be above than this point number 2, and it will be moving towards your right direction of your TS diagram. So it will be clear that you have to make some point, which is you can draw over there also. It will be no problem if your states are not given. So you can just mention over there that this is 3, and you can join this point over there. So this is a simple one. Okay.
Okay, sir. Okay, sir.
Okay, so now we also have to know that this cycle which we are talking about, Otto cycle, is the ideal Otto cycle. Okay, in which we have to assume many things. But whenever you are talking about the real cycle, which is your actual spark ignition engine, this TS or PV diagram is totally different. Okay, so we will also try to draw that PV diagram, that how this will be different from this PV diagram of your ideal cycle. So then you will get the better understanding what is happening in your actual cycle as well. Okay, so this is the clear PV and TS diagram which is shown over there. So you will get the clear idea for this type of thing. So you can also go to your book and you can see it. Okay, so now coming towards the Otto cycle, so which is your actual one. So here you can just delete this one, ideal. So this is the actual cycle. Okay, so in the actual cycle, there will be a compression stroke where there will be a compression will be happening over there. Then there will be a power expansion stroke. So in your expansion stroke, there will be a 3 different processes. So we will see that what are these different processes involved in it. So first you have to notice that here there will be 2 valves. This one is your intake valve, where you have to intake some air or your fuel mixture over there, and then here there will be a exhaust valve. Okay, from where after combustion exhaust gases will exit. Okay, so here there will be a spark over there, your spark plug. So whenever there will be expansion process, there will be a spark, then there will be a combustion also. Okay, so in your power stroke, there will be a three different processes will be happening over there. So we have to draw on the TS diagram also that how these processes look like. Then there will be exhaust stroke. So after there will be combustion process. So your piston will move towards TDC again, and all the exhaust gases inside your cylinder will exit from your cylinder as well. And then this is your intake stroke, from where you have to intake some air or fuel mixture inside your cylinder. Okay, so we will try to draw this on the PV diagram, so then you can get a better understanding of it. Okay, so we will start with the intake stroke. Okay, because first thing is that you have to intake some air and fuel mixture inside your cylinder. So after this, the process will be started. Okay, so for this state, we have to just draw one reference line. So you can just call this as a P atmospheric pressure. Okay, so I will give you an explanation. What are the purpose of this reference line? So this is your P atmospheric pressure. Okay, so make it clear that whenever there will be intake stroke, so you have to inject some air fuel mixture, and the pressure outside is P atmospheric, okay, and your inside, because there will be a vacuum, so once you have to intake some air fuel mixture, the pressure will be less than P atmospheric inside your cylinder. Okay, so it's mean that your intake stroke, for example, here your intake stroke will happen. So this you can call as an intake stroke over there. Okay, and after intake your pressure will go below this P atmospheric, and then your pressure will remain same. Okay, so this is your intake process. Okay, so this I am talking about the actual cycle. Okay, so this is not an ideal one.
सर ये दोबारा बताइए.
Okay. Okay, so here the point is that whenever you have to open the intake valves, the air fuel mixture will goes into your cylinder. Okay, so outside your pressure will be P atmospheric outside of your cylinder. Okay, but whenever you have to intake some air fuel mixture, because inside of your cylinder there will be a vacuum, and when this intake valves open, this pressure will be less than your P atmospheric pressure. It's mean that after intake your pressure inside the cylinder will be moved towards your towards down towards your the atmospheric pressure. So we have to draw this line like this. After intake there will be a decrease in pressure, and then when there will be an intake will be finished. Okay, so this pressure will remain same inside your cylinder. Okay.
Okay, sir.
Okay, so now this is your intake process. Now coming towards after this, there will be a compression process. Okay, because there will be an injection of air fuel mixture. Now this process will happen, which is your compression stroke. So we will see that after compression, the volume of your mixture will inside your cylinder will be decrease. Okay, so it's mean that this point you can just say this will come over there because it will go towards the decrease in volume. Okay, because it will be a compression process. And after compression there will be a spark over there, which is your power just initiation of your power stroke. Okay, so first in a stage of your power expansion stroke is the spark, which is your ignition. So you can say here this point will be ignition point, so I just denote with the IG. So this is the ignition point, and then there will be a combustion, okay, inside your cylinder. So, okay, the main important point is whenever we are talking about the previously we see that there will be a ideal cycle, Otto cycle. So, in the combustion, it will be a constant volume process. However, in the actual cycle, it will be not a constant volume process. There will be a slightly decrease in your volume, okay, and then after combustion process, your volume will be almost same over there. Okay, so this is called as an end of combustion. Okay, so here the ignition start over there, and at this point your combustion will be end. Okay, and after combustion there will be a expansion stroke over there. Okay, so it's mean that your expansion process will happen, and when there will be expansion process, it means your volume will increase. Okay, so and your pressure will decrease. So you can just make this point over there because your volume will decrease, your volume is increased and your pressure will decrease. Okay, so this is your expansion process over there. Okay, and then if you see that after expansion there will be an exhaust stroke. Okay, so it's mean that exhaust gases will exit after your combustion process. So you can just, and it will be happen just after your expansion. Okay, so you can just say that this point is your exhaust EVO, exhaust valve open. Okay. Okay. So after exhaust valve open, so what happened with your process is that again this will be go towards your intake, and the pressure will be equal over there points till the intake point, and then your cycle will be completed. Okay, so this is how your actual spark ignition engines PV diagrams look like. Okay, so if you see that for the ideal case, we make it very simple so that we can easily thermodynamically analyze the cycle for over simplicity. Okay, so if you have any question, you can also ask me. I will suggest you have to practice this by yourself, then you can get better understanding that what is happening inside your cylinder, or when there will be a 4 different processes. Okay, so now coming towards okay, so here it will be mentioned over there. So the ideal cycle, I already draw the TS diagram and PV diagram for this cycle. So you can draw it by yourself and you can compare. So first process is your compression process. Then there will be a constant volume heat addition process. There will be the asymptotic expansion process, and then there will be a heat rejection process in your ideal spark ignition engine or ideal Otto cycle. Okay, and you will get the clear idea by seeing this picture, which is from your book. So you can just compare these two. Here it will be shown over that how your actual cycle looks like, and here it is shown that how your ideal cycle look like, okay, for different processes. So you will get the comparison of this. Okay, so now another picture which is a clear idea that how you will get the different processes inside your cylinder. So this is your intake stroke. So at intake stroke, your intake valve is open, okay. Then the exhaust valve is closed, and your piston is toward your bottom dead center at this time when there will be an intake stroke. When there will be a compression process, your piston will move towards your top dead center, and your both of the valve, intake valve and your exhaust valve are closed at this time. Okay, and after this there will be a power store. Your spark will happen. Both valves are closed at this time when there will be a spark happens inside your cylinder, and then there will be a combustion process, and your piston will move after combustion process, move towards your bottom side. Okay. And then there will be exhaust door. For exhaust door, intake valve is open, intake valve is closed, and your exhaust valve are open. Okay, in order to exit the combustion gases from this port over here. Okay, and your piston is at your bottom dead center, and then it will move again towards the top dead center when it will be an exhaust door. Okay, so these are the different processes involved in your spark ignition engines. I hope you will get the clear idea of this one. Okay, so now coming toward one question. So you can, so it is mentioned over there, there will be a New Holland diesel tractor, has a 3-cylinder 4-stroke engine. Cylinder bore is 88.8 millimeter, stroke is 127 millimeter. Mean effective pressure is 32 Pascal. So you have to calculate piston displacement and net torque. Okay, so piston displacement is basically the volume displaced, which I already talked about this in the previous slide as well. So what you have to do is you have to find W net. So W net, we know that mean effective pressure into your area of piston, or you can say it would be inside your cylinder, or into your stroke length. Okay, stroke is given in your question. Area of piston you can easily find. You can say B, okay, which is your bore, or you can say D also. So it will be your diameter of your inner diameter of your cylinder. Okay, so area comes from there. Okay, and then this area in the piston into stroke is your volume displaced. Okay, so this will be the first part, and this will be your second part if you can multiply with the mean effective pressure, because mean effective pressure is also given. So this question you have to provide me the answer of 1 and 2. Okay, and you have to mention your ID as well, and then you can just send it to me on my inbox. Okay, this is a simple one. If you have any questions, you can also ask me.
सर
जी
सर हमारी जो पावर स्ट्रोक होती है इंजन की, वो हमारे क्रैंक शाफ्ट को मूव करवाती है ना, रोटेट करवाती है।
जी बिल्कुल, आपके उसी को मूव
तो
कराती है। और
सर
during fourth stroke there will be two revolutions in your engine, okay, because there are two power strokes. One is the compression one is the expansion one. So your crankshaft will rotate two times for
तो
one
सर
cycle.
ये जब इनटेक स्ट्रोक हो रही होती है तो ये वो हमारा पिस्टन नीचे कैसे जाता है?
जब इनटेक स्ट्रोक हो रही है उसके बाद तो आपके पास आएगा ही कंप्रेशन है ना आपके पास, क्योंकि आपका फ्यूल मिक्सचर तो एंटर हो गया, ठीक है, इनसाइड योर सिलेंडर। ओके, सो देयर विल बी अ compression part, we will see from the figure, okay, so that you will get the better idea. तो आप कह रहे हैं इनटेक के बाद हमारा पिस्टन टुवर्ड्स द बॉटम डेड सेंटर किस तरह जाएगा?
जी
ओके, सो फ्यूल एयर मिक्सचर आपका इनसाइड आया, ठीक है, इट्स मीन दैट योर एयर विल बी इनसाइड, योर फ्यूल विल बी इनसाइड, द वॉल्यूम विल इंक्रीज over there, so it's mean that your piston will move towards your bottom dead center. After this there will be a compression process, okay, because it will be a complete cycle. Okay, so if you can notice over there, so this will be from intake stroke, then there will be a compression, then there will be a power stroke. Okay, so in the power stroke the piston will move towards your top dead center to bottom dead center, and then this revolution will continues over there.
अच्छा सर, ये इनटेक स्ट्रोक की तो ठीक है, समझ आ गई। हमारे पास गैसेज अंदर आई तो हमारा पिस्टन चला गया नीचे। तो ये कंप्रेशनल स्ट्रोक में ये वापस ऊपर कैसे आता है?
इसको आपको
तो
मेरे
सर
ख्याल से मुझे एक सिमुलेशन दिखानी चाहिए थी, फिर आपको ज़्यादा बेटर अंडरस्टैंडिंग हो जाती। कि मैं आपको एक सिमुलेशन इसकी सेंड करूँगा ऑन योर थर्मोडायनामिक पोर्शन जो आपका बना हुआ है MS
ओके
Team
सर।
पे, so then you can get better understanding of it, that what is happening inside this cycle. Okay, another thing is that I think most of the students do not enroll by LMS. Okay, have you got the LMS enrollment key?
यस सर।
Okay, all of you have. Okay, if anyone do not have it, I will also share on that same thermodynamic group so that you will get it from there also.
ओके सर।
Okay, so I hope there will be no issue in solving this question because it is a very simple one. Okay, so I am going to leave now. If you have any question, you can drop me an inbox also. So I will give